which means that we're doing reactions outside the benzene now, okay? Until now, the 5 reactions that I showed you yesterday, they were all happening inside the ring, which means that the ring was involved, the aromaticity was involved. There was only one reaction we did side reaction, which we're going to do today also, and that was the reduction, the Clemenson and the Wolff-Kishner reduction. That's what we did yesterday. That was a side reaction because it had nothing to do with the ring. Okay, so, and actually the side reactions are interesting because you can do them even otherwise, but some of the side reactions are very specific to the ring. So I'll do the one that you've already done before, which is reduction. Okay, so we'll start with something we already know. And reduction is the Clemenson and the Wolff-Kishner, okay, that we'll write down. So here, if you have a ketone, I'll just write it like this, okay, so that you have both the reagents here because we've done this. So zinc, Hg, and then HCl, that's the Clemenson, and then NH2, KOH. This is the Wolff-Kishner, and both of them will give you the same thing, which is reduction of the ketone. That's it. And why do we have HCl versus KOH kind of thing? It gives you a little bit of a variety for reducing agents. Like, so if you want to work in an acidic medium or a basic medium, at this point, you may not really have to deal with it so much, but if you do, which means that if you have any functional groups that are acid sensitive, then you don't use the acid, or base. It depends, okay? So I don't think that's going to be so much of an issue for you. And one thing I want to tell you before I move on, the NH2, it's called hydrazine. Okay, I gave that name to you yesterday, but it's also written as N2H4. Okay, so just kind of letting you know, if you see that, don't think that, oh my God, I've never seen this before. Okay, so you have seen this before. It's just written differently. Okay, and you know that we do that a lot, okay, in organic or in chemistry. So that's the first reduction, and that is something that is known to you already. Now this is a new one, but the reagent is not new. So now we're going to take nitrobenzene. I'm going to treat that with LAH. That's an old reagent for you, and you can reduce that to an amine group. So until now, we've not actually added an amine group to a benzene ring. We learned how to add a nitro group to benzene ring, but not an amine group. Okay, actually, we haven't even learned how to add an OH on the benzene yet. Okay, so we're going to do that today, but we haven't done that. So we've only learned a few functional groups to add on the benzene ring. So now if you wanted to put an amine group on there, you'll first have to do a nitration and then reduce it. So it's a two-step process, okay? Another reagent you can use over here if you want, and you do want this, okay? Because you know LAH is a very powerful reducing agent. So if you have anything else on there like carboxylic acid or aldehyde or a ketone, the LAH is going to reduce those as well. Okay, so you can't really have such a strong reducing agent, okay, all the time. I mean, if you have only nitro groups, fine, go for it. But if you have something else, then you have to be careful, okay? So you can either use iron and HCl or tin and HCl, okay? And you get the same thing. You still get the same product, but, it's just a choice, okay? You can use different reagents here. Okay, the third one also but I just want to write this for you so that you have this in your notes and for your record. And this is for outside. This is for outside the benzene ring because remember, benzene ring itself does not get reduced. Okay, although we'll talk about that today. Again, I keep saying that because there is still stuff to do today. So if you take hydrogen and palladium, this is hydrogenation, so you can do this quite safely without much problems because the benzene ring itself does not get reduced even though it has the 3 double bonds, okay, in there. So these are all the reduction, okay, that you can do outside the benzene ring. So Clemenson, Wolff-Kishner, lithium aluminum hydride or the tin HCl, whatever you want to use to reduce a nitro group. And then simple hydrogenation. If you have an alkene or an alkyne outside, you can go ahead and reduce them as well. Okay, very easily. Okay, we haven't quite learned how to make a styrene yet. This is styrene, the one, the vinyl benzene, that's styrene, but I'm sure you can make it now because, you know, because you're so good. All right, so then number 2, oxidation. This is a fun one. And oxidation, you also know this oxidizing agent, and that's KMNO4. And here we make benzoic acid. You can also use chromic acid, which is also a strong oxidizing agent. You have to use a strong one. You can't use a weak one. Weak one will not take it all the way. This reaction is also known as degradation because it will degrade everything. Okay, so please note something, and I'm going to write this, but I will erase it because I don't want you to do this. It's a very common mistake to do this. Okay, that we forget where the carboxylic acid should go, and you end up writing something like this. But there is a difference between the two. You have an extra carbon in the bottom one. Okay, so this doesn't happen. The whole group is going to go away. Okay, so let me give you another example. If you take something even like this, which is a cyclohexane on the benzene ring, and you treat that with KMNO4, you will still get benzoic acid. And that's why it's called degradation, because everything will go away. The only time this reaction doesn't work is for this. And let me write it out and then show you what why it doesn't work. This carbon here is a tertiary carbon. Sorry, a quaternary carbon, not a tertiary. That's a quaternary carbon. And because it's a quaternary carbon, this reaction doesn't work. Which means that any kind of group. So if I had put a methyl group here, this reaction will not work. Okay, so I'm going to erase that. But otherwise, if it's a quaternary carbon, the reaction doesn't work. Now, I'm not that mean in the sense that I don't give you that one reaction that doesn't work, okay, for your exam. So I don't need you to memorize this fact. I just need you to know this in case you see that, oh, there's an alkyl group out here, but this is written as no reaction and I don't know why it's not working. Well, check your notes, okay? Because the quaternary carbons outside benzene rings are not going to get oxidized, which means what? It means that the primary will, so this one is primary, for example, the one on the top, this one is primary. Actually, it's secondary because it's got two things around it. So the only primary would be if you had a methyl group. And then this one is 1, 2, 3. So this is tertiary. So this will work. Okay. So the secondary and the tertiary carbons, they're going to work fine. Primary, secondary, tertiary. Okay. Primary, secondary, tertiary, you can oxidize, but the quaternaries, you cannot oxidize those. Okay. So this is the oxidation reaction, and that's it about oxidation. Now for allylic bromination, which you also already know from free radical reactions. So allylic bromination is, of course, the bromination on the allylic position. So here, let me write the benzene ring with the double bonds so you can clearly see what's going on. NBS, remember, N-bromosuccinimide was the reagent of choice. We did this in conjugation also, if you remember. This is how we made conjugated systems when we needed to synthesize them. So NBS. So allylic bromination. So the allylic point is 1, 2, 3. Remember, the third carbon That's the allylic position. There. So that's what you get. It's of course more stable also, but let me write another reaction here for you. Even if you had something like this, okay, and you were to treat this with NBS, there'll still be only one product. That's it, because that's the allylic position. And remember, bromine is very selective. When we were talking about free radicals reactions, I mentioned it to you that bromination, it's very selective, it's a slow reaction. And because of that reason, it decides where to go in a very calculated manner, if I can say that without sounding negative. On the other hand, if you were to take something like this and treat that with chlorine, so this is not bromination, obviously. So if you were treat this with chlorine, now chlorine is a little bit more fast reacting, so you will end up getting two products. Generally, as you know, the secondary radical is more stable. So maybe you get a little bit more of the first one, but you're also going to get the second one, okay? Because chlorine is not all that selective. So one of the nice things about brominations and chlorinations outside the benzene ring is that now you actually have a leaving group outside the ring. Okay, so you just managed to create a leaving group, and now you can do all sorts of reactions outside the benzene ring now. Okay, so which means if you wanted to have the bromine as a leaving group, make an ether if you want, or add, carbons to it like alkynes, like we have done before, any kind of an SN2 reaction now you can do because now you have a leaving group. Okay, so depending on how many carbons you want in the chain, I used ethyl benzene, but you could have used toluene. Toluene has only one carbon. So, you get the bromine only in that one location, and you don't have any additional carbon. So then you can kind of figure out what you want to do from there. Okay, so allylic bromination really has a lot of synthetic applications, and so it's very useful reaction. Okay, so that is the three reactions that we have on the side chain. Yeah, and I know if you were thinking there should be more, there isn't any more. Okay, they're all the side reactions. Actually, okay, let me show you what I mean. Okay, by that, let's go ahead and make styrene. Okay, because I told you we could make styrene. So this is it. So for example, once you get this, now you can do T-butoxide on this one, and then get styrene or vinyl benzene, right? So this reaction is happening outside. And that's where, organic chemistry is a little bit more comprehensive than any other chemistry, because now you have to bring back your E1, E2 reactions from organic one, okay, in order to do these reactions, which I strongly suggest that, you don't lose that yet, okay? Don't burn your notes yet. Keep all the notes from organic one, go through the alkenes and all the reactions we've done, because here now, once you have an alkene, you can do any number of reactions on alkenes. And I expect you to know all of those reactions, okay? Because we've done them already. And that's why, organic 2 is not separate, okay, from organic 1. I think it should be like a whole big course, organic chemistry. That's it, part 1, part 2. But otherwise, it's expected that you know all these reactions now on alkenes and alkynes and substitution reactions. So anyhow, so that's the side reactions for benzene. I want to do a couple more reactions. And one of them is reduction on the benzene ring. Okay, so this one. And I've been saying until now, oh, benzene doesn't reduce, but it can in very, strenuous conditions. So if you take a benzene ring, you treat that with hydrogen, and palladium, of course, you need a catalyst, but the pressure has to be 25 atmosphere or more for you to do this reaction. Remember, the pressure on you, generally, atmospheric pressure is about 1 atmosphere. Okay, so 1 atmosphere is, doable. And on exam days, you'd probably increase this to 1.2 for you. But otherwise, it's, 25 atmosphere is like 25 times of that. So you can imagine how much pressure you need. And then you end up getting reduction, which now, after the first one, not a problem anymore, because after that, there is no more aromaticity, okay, in there. Benzene, you started that with an aromatic benzene, so that's an issue because that's very hard to reduce. But once you've reduced it, now you just have a normal diene. And once you have that, then you don't really need high pressure anymore. And you can use whatever metal you need. And usually people don't stop in the middle. And you can go on and, just get all the way to cyclohexane. Not that you want to, but, if you wanted to, you could. Because I would just buy cyclohexane from the store. So that's one possibility. The other thing is you can go directly. Okay, so if you have excess of hydrogen in palladium and at 25, at some point my pen will start writing again. Palladium 25, atmosphere pressure. The downward arrow shows you pressure. And so you can go directly there instead of going step by step because it's really hard to isolate anything in the middle anyway. So you might as well go all the way. So this is one reduction, which nobody does. Nobody does the reduction on benzene ring because it's very hard to do. However, there is another reduction, which I would like you to remember if you can. And this is a new reagent, but it's not a new reagent. You've used this reagent before. This is sodium, ammonia, ethanol. And you get very, very specific reduction in this one. So take benzene, treat it with sodium or lithium, ammonia, and ethanol. Perfect. So you did this one, same reagent, and you were able to make a trans alkene. That's the, yeah. So this is an old reagent, but so that's why it's okay, for us to talk about this because it's not a new reagent I'm teaching you. I don't think any of the reagents we've done so far, anything is new. It's just that you're applying them in a different way. Okay, so the thing about the Birch reduction is that the Birch reduction is very specific to give you the not conjugated alkene, okay? Because you can get, if you do reduction, you can get either alkene number 1 or alkene number 2, but here you're getting only alkene number 2, which is the non-conjugated one. Okay, so it's a very specific kind of a reduction, okay? The good thing about all of this that we're doing right now, at least for today, there is, no mechanisms. There were some mechanism that I showed you for the monosubstitutions, which was pretty much resonance. We haven't really, it's not a whole entire mechanism. It's just resonance. And then, coming back from resonance to give the final product. So it's a very simple mechanism and only one. You can use that mechanism for all monosubstitutions. So here also, don't worry about the mechanisms, okay? Focus on the reaction, what it does, what kind of products do you get, very specifically, okay? So again, I always suggest you make a chart of your reactions, so make a page of it. Klein has them at the end of the chapter, so you can use those. But, my recommendation is make your own, okay? So you have it in your own handwriting. Okay, so that was Birch reduction, okay? And then I think this is the last thing. Last reaction, which is substitution reactions. You know, the funny thing about the stylus is I can't even say that it's running out of ink because it's not running out of ink. Now it's running out of battery. That's the only thing you can say. Okay, substitution of benzene rings. But mine has full battery. I don't even know why it's not writing sometimes. So back when we were doing substitution reactions, I said to you that you cannot do this. And I taught you specifically a couple reactions, okay? These were from back in organic 1, okay? So I said to you, you can't do these reactions because the nucleophile will not attack anything. That itself is a nucleophile, okay? So it's not going to happen. Nucleophile cannot attack a nucleophile. So we wrote these two reactions back in organic 1, but things change, okay? Because we learn. And now this is the reaction that we are going to write. And in this case, we're going to treat this with sodium hydroxide. But this is at a very high temperature and under pressure. So you're creating very harsh conditions, then only you can do a substitution. So normally, if you wanted to do substitutions at even high temperature, like 100 degrees Celsius, you cannot do that, okay? The sodium hydroxide here, it's called fused sodium hydroxide. So sometimes you might see it like that, which you get only at very high temperature and pressure, okay? So there are two substitution reactions that are possible on benzene ring. So Cl, take a similar leaving group, chlorine or bromine, it's fine. And then NaNH2, which is sodium amide. And this is also done in very harsh conditions with liquid ammonia. And now you get aniline. So you make phenol and aniline. The thing about these two reactions is that they're both only industrial, which means you cannot do them in the lab. In the lab, you can't create those kind of conditions with a high temperature and pressure that you can make phenol. So in the lab, we make phenol in a different way. Actually, nobody makes phenols. Generally, you buy the phenol. But if you did want to convert a group on the benzene ring to an OH group, there are other ways to do it. Okay, and you don't know them now. We will do them later on. Okay, right now we have not done that. What I'm trying to say is also don't give that to me in a synthesis yet, okay? Because we haven't done any other synthesis yet for phenol. This is the only synthesis you know so far. For aniline now, this is the second synthesis, okay? Because the first one was where you put the nitro group and you took the nitro group and you can reduce that, okay, using LAH. So we just did this over here with the reduction. So this is the second synthesis now that you're learning for aniline, okay? The nitro group synthesis is more like a lab synthesis, okay? The amine group, the aniline reaction that I wrote just now with the substitution, this is more like an industrial synthesis. So these two substitutions, you need to know that you can do these reactions, but you also need to know you cannot do them in the lab, which means that for us, it's practically impossible, okay, for us to do these syntheses, which means that you also should not be giving me these syntheses, okay? Eventually, right now you can. If I ask you for a synthesis of phenol, you can write this synthesis, no problem, okay? Later on, we're going to change, but right now you can write me either of these syntheses and I'll be fine, okay, with that. So these are the two reactions we can do. Substitution reactions, okay, that we can do for benzene ring. So that brings us to the end for this little portion. But now I would like to do a couple syntheses here for you so that you can see that even though we have not done any dye substitutions, we've done only the mono substitutions and the side reactions, there are still some syntheses that you can do. Okay, so let me see if anybody has any questions at this point. So again, make sure you write all your reactions on one page so you have, everything together. Again, don't use that as a cheat sheet. Use that as a memorizing thing, okay, for yourself. Okay, so let's do couple syntheses at least, okay? So you can see how we can do this. So let's go from here to anisole. Anisole is methoxybenzene. So let's see how to make methoxybenzene from benzene. So here, first step, bromination. Don't forget to write the catalyst, okay? Because without catalyst, it's not a reaction at all. So make sure you write the reaction. By the way, just to kind of take you backwards a little bit, and I'll write that on the side, is the retrosynthesis, okay? Just a little bit of retrosynthesis here on the side. So to make methoxy, you need to have an alcohol group on there, right? Because that's how we've learned how to make ethers. And then alcohol group, you know that you can get that from bromination, okay? Because we've just learned that also. So that's exactly what I'm doing here right now, is to make, put the bromine on there, and then we'll go forward from there. So that's bromine. Then we'll do sodium hydroxide. And you can just write heat and high pressure. See symbols, big thing, in chemistry and in life, everywhere. Symbolism is really important. And then get the OH. Now you can do this in 2 steps, or you can actually just do this in 1 step. And you've done this, I don't know how many times for me before, is you treat this with sodium first, and then you will treat that with a substrate, right? So the sodium will take away the hydrogen, you create an oxide. Once you have that alkoxide, which will be phenoxide at this point, so that phenoxide now will become your nucleophile, right? So the first one will give you this. I'll just write it on the side here. That's what you're getting, okay? And so I gave you that, oh my God, long time ago. I don't know, in which of the homeworks, you had that in there. So a simple synthesis where you have benzene reactions also and side reactions as well. Alcohol reactions also, because we've done alcohols before. So something like this. Okay, so let's do another one. So here we're adding CN. CN, if I asked you like way before, like even in chapter number 7 for substitution reactions, you would tell me, oh yeah, if I wanted to make a CN kind of a thing, I would need to have a leaving group on here, and cyanide would be my nucleophile. You would have done this for me even before, okay? Even last semester, you would have done that. So, which means that we should be trying to focus on how to make this, all right? And how to make that, let me go ahead and remove that arrow because that's quite a misleading arrow. We can get that from toluene, because we know that this carbon is the allylic carbon. So we can get bromine there without any problem, okay? NBS, that should work. And how do you get toluene? You can get toluene from benzene by using CH3Cl, AlCl3. So not that complicated. I just finished that even in retrosynthesis. I don't even have to write the forward synthesis for it. I can. I don't know why I'm writing this. Maybe I feel like writing. Maybe it's a short class and I will miss you for the next 4 days. Could be that too. NBS. So then there BR and then CN. I can do pretty much any kind of substitution that way, you know. So another reaction that is on benzene and then outside benzene rings. Okay, so you can see that, what you know, it's a lot. It's a lot. Okay, because these are not a couple step synthesis now. These are getting into 3 or 4 step synthesis. So there are reactions you can do in 1 step, 2 steps. And now you're getting to know so many reagents that you can do this in, more than 2 steps. Okay, so you should be comfortable that you know a lot in organic now. We are so far ahead. So that is it. That is all I had for you for this portion.